Hello everyone, in this video we'll be discussing lipid transport. We'll be starting our discussion by first discussing cholesterol synthesis. Now the most important step to know in cholesterol synthesis is going to be the conversion of HMG-CoA to mevalonate with the enzyme HMG-CoA reductase. And remember that statins are going to be inhibiting this enzyme. Now this is all going to occur in the liver, and bile acids can be produced from cholesterol, and bile acids are going to be excreted into the duodenum where they can then be emulsifying fats. Now, once bile acids reach the terminal ileum, they can be recycled. And remember that bile acid sequestrants like cholestyramine can inhibit this. And so ultimately, we're going to have lower cholesterol levels because we will have to consume more cholesterol to produce bile acids. Now, we can synthesize cholesterol in the liver, as we just discussed, and we can also absorb cholesterol in the small intestine when we consume it in our diet. Now, the consumption of or the absorption of cholesterol into the small intestine can be blocked by ezetimibe, which is going to be a drug that is going to inhibit the absorption of cholesterol in the small intestine, and therefore it is going to lower cholesterol levels in the body as a result. Now, cholesterol and triglyceride can be grouped into chylomicron, as you can see here, and chylomicron is going to be an example of a lipoprotein. Other examples of lipoproteins are going to be HDL, VLDL, IDL, LDL. So these are all going to be lipoproteins. A lipoprotein is basically a transporter that is going to be transporting lipids in the blood. Remember that lipids are not going to be soluble within the blood, therefore they're going to need transporters, and lipoproteins are going to be functioning as the transporters for lipids in the blood. Now, as you can see from this image, chylomicron is going to have something called ApoB48 on its surface. ApoB48 is going to allow the chylomicron to be secreted from the intestines into the blood. A mnemonic that you can use to remember the function of ApoB48 is that he ate cholesterol. Remember that chylomicrons come from our diet, and ApoB48 has the word ate in it. So this can remind you that B48 is associated with chylomicrons. Now, once chylomicrons are excreted into blood, they can encounter HDL, and HDL can put ApoC2 and ApoE on the surface of the chylomicron. Now, the function of ApoC2 is that it is a cofactor for lipoprotein lipase. So with ApoC2, once the chylomicron encounters lipoprotein lipase, this enzyme can cleave fatty acids from the chylomicron, and it can convert the chylomicron into a chylomicron remnant. And once this occurs, we're going to remove ApoC2 from the surface. Now we're just left with ApoE and ApoB48. Now the function of ApoE is to facilitate the binding of the chylomicron remnant to the hepatic remnant receptors, as you can see here. So it is basically going to function to uptake the chylomicron remnant into the liver. So ApoE, remember the E in the word remnant, we're going to be facilitating the uptake of the chylomicron remnant into the liver by the interaction with the remnant receptors. Now, E can also stand for everything because almost every lipoprotein except LDL is going to contain ApoE on its surface. So therefore, we're going to be able to uptake these lipoproteins into the liver with the remnant receptors. Now let's focus on VLDL. VLDL is going to be synthesized in the liver, and it is going to contain ApoB100 on its surface. ApoB100 is going to allow VLDL to be secreted from the liver into the blood. Fibrates, niacin, and fish oil can inhibit the secretion of VLDL from the liver into the blood. Once VLDL is secreted into the blood, HDL again can put ApoC2 and ApoE onto the surface of VLDL. Now remember, ApoC2 is a cofactor, C for cofactor, for lipoprotein lipase. So now this enzyme is going to cleave fatty acids from the VLDL, converting it to IDL. Again, we're going to be removing ApoC2 from the surface as we do this step. And once we have IDL, IDL can be converted into LDL with the enzyme hepatic lipase. And this is going to happen when we remove fatty acids from the IDL, and that way we can convert IDL into LDL. And when this step occurs, we're also going to be removing ApoE from the surface of IDL. And remember that LDL is only going to have ApoB 100 on its surface. Now, we don't have to convert VLDL and IDL into LDL. These lipoproteins can be uptaken by the liver through the remnant receptors because they have ApoE on their surface. Remember that ApoE is going to facilitate binding to the hepatic remnant receptors. So because VLDL and IDL have ApoB on its surface, we can uptake these lipoproteins into the liver. Now that we have LDL left, the function of B100 we said was to excrete VLDL from the liver into the blood. The second function of ApoB100 is also to facilitate the binding of LDL to the hepatic LDL receptors. So here we have the LDL receptor on the surface of the liver, and we can use ApoB100 to facilitate the uptake of LDL into the liver through these receptors. And remember that PCSK9 is going to be an enzyme that is going to break down LDL receptors. And so we can use a drug class called PCSK9 inhibitors that is going to inhibit the removal of these LDL receptors from the surface of the hepatocytes. And so therefore we can reduce LDL levels within the body because we're going to have more of these LDL receptors that will be able to uptake LDL into the liver. So that is the basis of lipid transport. I hope this video makes sense. Thank you for your time.